So there are 6 limitations. If a slab system satisfies all of these limitations, then we can say that this direct design method is applicable for that system. If any of the limitation is not satisfied, then this direct design method is not applicable for that type of slab system. So we will go one by one into these limitations. So the first is there must be at least 3 spans in each direction. If there are fewer spans, the interior negative moments tend to be small. So the limitation is that we can apply this direct design method to only those slab systems which have at least 3 continuous spans in each direction. So we can see in this picture, in the first we have only one panel, one span, here again one span in this direction, here one span in this direction, but here we have 3 consecutive spans. So the limitation is there should be at least 3 consecutive or 3 continuous spans. So in this direction this is okay, but here it is not okay. So we cannot apply direct design method to such type of slab systems. In the right picture we can see that in this direction there are 3 consecutive spans, and similarly in this direction there are 3 consecutive spans. So for such type of slab system the direct design method is applicable. So this is the first limitation. Okay, second is panels should be rectangular and the ratio of longer to shorter span within the panel must not exceed 2, otherwise one-way action will prevail. So the direct design method is only applicable for two-way slab. So the slab must be two-way. So all panels of the slab system must be two-way slabs. If any of the panel has one-way action, so then again the direct design method will not be applicable. Okay, next is the third limitation is the successive span length center to center of support in each direction must not differ by more than 1/3 of the longer span. So what it means? For example, in this slab system we have L1, this L2, we can say this L3. So for example, this L1 is the longest span. So and it has a length of 6 meters. So the next span should lie, or the difference of the panel length of the next span can be only 1/3 of the first span. So 1/3 of the first span, or 6 meter, can be 4 meter or 8 meter. So the length of this panel can lie between 4 and 8. So if the length of this span is, for example, 9 meter, so the difference of these two span lengths will be more than that of 1/3. So in that case this direct design method will not be applicable. So the difference between the length of the consecutive panels cannot be more than 1/3 of the span of 1/3 of the longer span. Okay. So the next fourth is load must be uniformly distributed with the unfactored or service live load not more than 2 times the unfactored or service dead load. So the ratio of live load to dead load should be less than 2, and the load should be uniformly distributed on the slab. So this might be confusing that in case of slab system sometimes we have walls on it, so that is not a uniformly distributed load, that is a line load. So if the line load is on the beam underneath the slab, then it is okay. But within the panel, there should not be any point load or line load. So on the slab, there should be only uniformly distributed load. And the ratio of live load to dead load should be less than 2. And if all the other limitations are okay, but there is a point load acting on the slab, then this direct design method is not applicable. So this limitation should also be satisfied. Okay, next is columns must not be offset more than 10% of the spans in direction of offset from either axis between center line of successive column. So the offset of the column from the line of columns should not be more than 10%. 10% of the span of the columns. For example, so this is the line of columns, and we have one column which is offset from this line. So this offset should not be more than 10% of this span. So for example, in this case, this span is 10 meter or 10 feet. So this offset should be 10% of the 10 meter, mean it should be less than 1 meter. So the offset of this column cannot be more than 1 meter. If it is less than 1 meter, then it is okay. If it is more than 1 meter, then it means this limitation is not satisfied. Okay, the last limitation is for two-way beam supported slabs. Relative stiffness of beams in two perpendicular directions must satisfy the minimum and maximum requirements given in ACI 8.10.2.7a. So this is the actually reference number at which location of the ACI code this specification is specified. So the limitation is the stiffness ratio, flexural stiffness ratio in two perpendicular directions. Their ratio must be between 0.2 and 5. So here alpha F1 is average flexural stiffness ratio in direction 1. So we can assume any direction as direction 1, so preferably longer direction, and alpha F2 is average flexural stiffness ratio in direction 2, so preferably shorter direction. And alpha, this is actually the flexural stiffness ratio of beam to slab. So this is flexural stiffness of beam and this is flexural stiffness of slab, where ECB and ECS are modulus of elasticity of beams, and ECB and IB are the modulus of elasticity and second moment of inertia of beam respectively, and ECS and IS are the modulus of elasticity and moment of inertia of slab respectively. Okay, here the question is how we can find this IS and IB. So once we have IS and IB for the beams of the panel, then we can calculate alpha F and this ratio. Okay, as we know that in case of monolithic construction, we do not consider beam as a rectangular section. We do not just consider the beam, this rectangular part. We also consider some part of slab as the part of beam. We assume that this portion of the slab also act as a beam or flange of beam, which is under compression. So the question is how much length of this slab should be considered as the part of beam. So there are limitations or there are specifications in ACI code. For edge beam, this projection or this part of the slab should be smaller of HB or 4 times of HF. So what is HB? HB is actually the distance between the soffit of slab and soffit of beam. So this distance is HB. For example, if we have a beam, the overall depth of beam is, for example, 500 millimeter, this, and the thickness of slab is, for example, 100 millimeter. Then this HB will become 500 minus 100, 400. So this is HB. And 4 times HF, this HF is the thickness of slab, so it's 4 times. So we will use the smaller value out of these two. So the smaller value will be the projection or the part of the slab which will be considered as beam. So this is for edge beam, and for interior beams the same will be considered on both sides, because in case of edge beam we have slab only on one side, but in case of interior beams slab exists on both sides. So on both sides we will select HB less than equal to 4 times HF, and here again on this side HB less than equal to 4 times HF. So once we will add this and with this BW width of the beam, so it will become, for example, HB is the governing value, so it will become BW plus HB on one side and HB on other side. So it will become BW plus 2HB, this one. Similarly, if this 4 times HF if this goes, then it become BW plus 4 times HF plus 4 times HF. So it will become BW plus 8 times HF. So we will select the smaller value out of these two. So we can see this BW plus 2 times HF, it should be less than BW plus 8 HF. So the smaller out of these two value will go, and it will specify the width of flange of beam. So once we have this width of flange and the depth of beam, then we can calculate IB. Okay, next is section considered for moment of inertia of slabs. So in case of slabs, again there are two different scenarios for edge beam and interior beam. In case of edge beam, we have slab only on one side, so the width of slab that will be considered for calculating the moment of inertia of slab will be this one, from the center of the support to the center of the panel. For example, if we have a slab system, like this, similarly it is continuous on this direction as well as in this direction. So for edge beam, first of all we need to consider this center line. So if we are considering this one beam, so this is the center line of the column. So from the center line of the column up to the center line of this panel plus this projection, which might be equal to the half of column width, or if there is a projection of slab like this, so that portion can also be included. So this much length will be considered as a width of slab, which should be considered to calculate the second moment of inertia of slab. So we can see that this is the length of half panel plus this one is half of the column width. So actually from where the slab starts up to the center of the span of panel. So this is actually B width. So we have B, we have H. So second moment of inertia will be B H cube over 12 for slab. So this is for H beam. For interior beam, we have slab on both sides. So from the center of the support, we will consider half panel length on this side and half panel length on this side. This L2 by 2, L2 by 2, where L2 mean the transverse direction of the beam. जिस डायरेक्शन में बीम है उससे, फॉर एग्जांपल ये बीम की डायरेक्शन है तो उससे ट्रांसफर डायरेक्शन में ये स्पैन, ये L2 by 2 है, L2 by 2. So in that case this will become B. So once we have B and H, so we can calculate this second moment of inertia of slab. So once we have the moment of inertia of slab and beam, we can calculate the stiffness ratio, flexural stiffness ratio, and we can check the limitations. Number 6. Okay, let's solve one example to check the limitations of DDM, to check whether this slab system can be designed using direct design method or not.